And is a screen sharing okay?
We're seeing the header for your web browser. If you don't care about that, then we're good.
Okay, I think that's okay.
Okay, so go right ahead. Our
All
next
right,
speaker is Yong Hoon Chung from the University of California at San Diego.
thank you for this opportunity. And in this talk, I'm going to talk about what the role of object files in visual working memory is, and that it can facilitate feature integration over longer time scales for moving objects. A lot of visual working memory studies often primarily use static and single feature stimuli, such as this change detection task or the continuous color report. But when we encounter an object in real life, we actually see it in many, many different states. And this is because of its features dynamically changing around due to different angles, lightings, viewpoints, and etc. Some previous works on dynamically changing stimuli report that there was some sort of a perceptual lag when tracking multiple objects for changing features, and this study tested for spatial frequency, orientation, and spatial position. People's memory lags behind the current state, or when they're asked to report the ending state, they report a little bit towards the past. And this lag seems to get progressively greater with larger set size. There's also work on temporal integration. This study showed participants a dot that is changing its size across time, and as participants report the average size of the dot at the end, they found out the performance is basically the same as presenting many different size dots all at the same time. So they basically found out that people are able to temporarily integrate the information. But these previous studies used changing stimuli that were still stationary. Now the question is, how will motion influence this? And this is especially intriguing because motion often induces features to change around in real life. For example, if you track a toy car that's moving across the floor, just like that, so it's moving around and it's stopping right there, you can actually see that if you zoom into that specific portion of the car, it begins with somewhat of a darker red color, and it ends with somewhat of a lighter red color. But you're not necessarily going to perceive this as having two different colors. You're going to integrate this information together to have a stable one red toy car representation. So although the features are changing around because of motion, when you suspect something is part of an object, or when you generate an object file, we try to integrate all this information into one single object representation. On the contrary, when the car is completely static on your retina or stationary, the features of the car is not really changing. In fact, it doesn't really change at all. So as you can see in the world, only moving stimuli tend to quickly change in features. Then again, how will motion influence visual working memory for changing stimuli? More specifically, if the stimuli that are continuously changing features are moving around, will it enhance or decrease the perceptual lag? And also, will it facilitate feature integration? So we can test this out by using much simpler stimuli, such as a color dot that is either moving around on the screen or stationary on the screen, while the color of the dot is continuously changing around. And we ask participants to report the ending color at the end. This is just a quick demo of the experiment. I'm going to go more into how the stimuli were generated later on. And this is our prediction. When the dot is stationary and changing its color, this is somewhat unnatural in the world. And people will perceive it as just color changing, like painting it over and over again. This will not result in integration, but just simply updating the colors. And when asked to report the last color, people report the actual last color that they thought they saw. However, when the dot is moving around and changing color, this is somewhat common in the world. So people will perceive the dot as one object that is continuously changing its color. This will induce the temporal integration of the colors, such as averaging of the colors, just like how you did with the toy car demo. And this will cause the representation to be seemed more lagged because people are incorporating the past color more, but more precise because people are averaging many noisy color representations. So this is our experimental design. There were two main conditions, stationary condition and the moving condition. And we also varied the set size 1 and set size 2, to see how set size influences this effect. So now to the stimuli. For the movement, the display time was randomly jittered from 2.5 to 3.5 seconds. And there were two dots presented on the left and right sides of the screen each, while participants were fixating in the center cross. And two half-circular invisible paths were preset on the left and right sides to ensure equated visual acuity. In the moving condition, dots were randomly moving around on the path. In the stationary conditions, dots appeared at random location of this path. For the colors were continuously changing 2 degrees per frame towards a clockwise direction in the preset color wheel that our lab uses. In set size 1, there was 1 black dot and 1 color dot. In set size 2, there were 2 color dots. And after 1 second delay, participants reported the final color of one of the dots using a same continuous color wheel that was used for the stimuli generation. And this is the demo again. So you can see that this is the moving condition, set size 1. And this is stationary condition, set size 2. I'm just going to wait to see the moving condition one more time. And this is the set size 1 moving condition again. For the analysis, the color error was calculated by subtracting the actual target color from the reported color. So if the target color was 45 and participants reported 30 degrees, the color error would be negative 15. And this means that negative value for the color error indicates lag, or participants reported somewhere in the past, and positive value could possibly indicate some sort of a future extrapolation. And this is the data. We plotted the color errors, and there are 2 main components in the data, lag and precision. And we measure these components using non-parametric circular statistics. So for the lag, this is the distribution mean shift from the 0 degree line, which means more negative shift indicates more lag, or participants reported somewhere in the past. Precision is how wide the distribution is, or standard deviation, and higher standard deviation is worse precision. If feature integration happens in the moving condition, we expect the lag to be larger and precision to be higher. So we can also look at the data by looking at the bar graph. So first, the lag, or the mean shift. When you look at the stationary condition, you can actually see that there's some sort of a positive shift going on, which might indicate some future extrapolation, but I'm going to go more into this later on. But the effect size seems to be really small, and it doesn't seem to be changing at all with the set size. Now, if you look at the moving condition, there is indeed negative shift going on, meaning participants reported somewhere in the past, or there was a lag going on. And this lag seems to get larger with larger set size. If you compare the stationary versus the moving, there's more negative shift going on in the moving condition, and the same trend follows in set size 2. We can also look at the precision data. And you can see that in both stationary and moving condition, the precision gets worse with higher set size, which aligns with all the other working memory studies. But interestingly, when you compare the stationary versus the moving condition, you can see the standard deviation is lower in moving condition, meaning the precision was better and higher in the moving condition. And same trend follows in set size 2 as well. So in summary, we found increased lag in color memory representation when participants were tracking moving dots, and also increased precision when dots were moving around. So going back to our prediction and the discussion, there was lag found in moving condition, and with larger set size, there was greater lag, which aligns with the prior studies. And it seems like there's almost possible future extrapolation going on in the stationary condition, and it is possible that participants could have looked at the same response color wheel and inferred a change and reported the future. But this could also be just baseline error towards clockwise directions, since it's only around 3-ish degrees, and also does not change at all with a varying set size. But regardless of whether this is true or not, our data still shows that there was more lag in moving conditions compared to the stationary condition. For the precision is lower when set size increased, which aligns with prior studies of working memory. But precision also seems to get better when dots are moving around. Now, this aligns with our prediction of integration. Because there was an integration and temporal averaging when dots were moving around, there is more lag, or there seems to be more lag, because participants are incorporating the past colors, but better precision because they are averaging many noisy color representations. Now, because the moving condition and the stationary conditions are very different, it is possible that some sort of lower level differences between moving and stationary stimuli also contribute to the results. And to test this, we plan to compare 2 motion conditions, one designed to induce continuous object perception and one designed to break the object file. And there are previous demonstrations that have shown how to utilize different motion manipulations to break continuous object perception. And one of them is this implosion manipulation. So basically, in the continuous condition, the stimuli would move behind the occluder continuously, just like how a real object would. In the breaking condition, however, the stimulus all of a sudden disappears as it hits a occluder, then pops out on the other side, possibly breaking the object file and breaking the integration. This is still ongoing. We were running some pilots, then we had to stop, and now we're trying to do it online. And thanks to everyone in the lab who helped me through this project, and thank you for your attention.
Okay, thank you for that talk. We've got a number of questions that just popped up. So let's start with Klaus Oberauer again. It seems like your precision at set size 1 was way worse than in usual visual working memory tasks, where it is around 10 to 12 degrees. Do you have a direct comparison to static, non-changing stimuli?
In this specific experiment, we don't have the static non-changing stimuli condition, but yes, compared to other studies that's reported, it seems like it's worse here, which could possibly be explained by the changing stimuli, right? Because it's continuously changing, there may be more noise going on or more uncertainty going on.
Okay, so unless Klaus Oberauer has something else to say about that, let's go to Nelson Cowan, who asks, could the smaller precision with movement occur because of an edge effect?
Is that clearer? I could explain what I mean.
Yeah, sorry, I'm not very familiar with the edge effect.
Well, the idea would be that, let's say if a reddish thing turns to a greenish thing, then the fact that it was preceded by red gives it a contrast. So then you know the greenish thing isn't really red. It's different from red. And the prediction would be if you look at the distribution, it wouldn't really be symmetrical. It'd be skewed away from, I think, skewed away from the previous item, or skewed, yeah, I think away from the previous item. I know it's shifted toward the previous item, but at the same time, I'm wondering if having something that occurred right before it gives you a range of colors that you're not going to actually use, so that it squishes the range of available colors to interpret what you see. Since color is very comparative, in perception, color is very comparative, and there are all these mistakes about buying the wrong paint because when you get it home, it's in a different context and it doesn't look at all the same. So could that kind of contextual effect actually reduce the precision? I mean, increase the precision, reduce the...
I see. So basically, if the colors were shown before are irrelevant, then participants can infer that those are not the colors and be more skewed away from those.
Yeah, well, at the same time, I know that the whole distribution is shifted toward them, but as it shifted, did you look at the shape of the distribution? Like maybe it's asymmetrical. At the same time, it's shifted toward them, asymmetrical away from them, and so more skinny,
Right, maybe. I don't clearly remember seeing the symmetrical or asymmetrical for the distribution, but I think it is possible. The thing is, if the colors were randomly changing around, like from green to red to yellow, then that effect might be more profound in this study. But because the colors were continuously and smoothly changing around, I feel like it's more of integration in the similar features or similar colors towards the end, maybe. And also the question would be, why wouldn't that happen at all in the stationary condition then, right? If that is really the only effect that's driving this precision difference.
Yeah, I mean, that's a good question. It's hard for me to imagine that averaging a bunch of different colors, gives you more precision itself. That's the part that's counterintuitive. Like if you'd found less precision, you would have had there might have been a similar kind of explanation about integrating, so I'm puzzling about that. That's all.
Yeah, that's a really good question. And it is also, the intuition is that because averaging of many noisy representation should give a better precise measure. But yeah, that could be somewhat unclear, and we could investigate that more.
So to piggyback on that question, I wonder if you could vary the speed of the color change and get at whether this is really about a time lag versus the change in the color?
Yeah, that's actually a really good question. We actually have another version of this study, which is not presented on the slides for the time, because of time. But in the second version, we made the color change 1 degree per frame, not 2 degrees per frame. So it was half the speed of the color. We actually found the lag seems to be, the magnitude of the mean shift seems to be similar to this version where it was 2 degrees per frame changing. So it seems like it's not necessarily the time or the time frame or the color speed change of the speed of the color change that matters. It seems like it's more of certain features that are similar that are being integrated. Since even though the color speed was varied, the similar mean shift magnitude was observed.
Okay, so there's one more question stemming from this talk, and then we'll open general discussion. Ronald Vandenberg asked, I assume that subjects were fixating the center of the screen during the experiment. Do you expect the same results if they were asked to follow the target in the moving condition, such that in all conditions, the stimulus would be close to stationary on the retina? This could obviously only be done for a set size of 1.
Yeah, that's a really good question. And yeah, I guess I don't have one clear prediction of what will happen to the data if participants are tracking the movements. Yeah, I mean, because the dot was randomly moving around, maybe it